Okay, I'm really happy to introduce Baris Kasikci from right now University of Michigan, and in a year he's going to move University of Washington as associate professor. Baris got his PhD from EPFL, worked with George Candia, and did some really great systems work, and his goal is to try to make computer systems reliable and performant. And for his work, like they had done, and before that, also before he went to Michigan, he also worked at Microsoft Research Cambridge in the UK for a little while, and so has done a lot of great work. I think he's one of the really superstars, young superstars in the systems area. And his work is really recognized by a lot of things. He has won the NSF Career Award, the Microsoft Research Faculty Fellowship, and also many best paper awards, one from OSDI, and many from micro top picks and so on, right? So, Baris, we're really excited to have you, that you'll be able to give us this talk over Zoom. So without further ado, let's hear from Baris.
All right, thanks so much, Anok, for that very kind introduction. Do I come across clear? Do people hear me well? Okay, awesome. Well, first of all, thanks a lot for inviting me, and thanks for giving me the opportunity to do this remotely. So I was supposed to be there. Well, okay, before starting here, so this complex list of affiliations, as Shandok mentioned, I'm currently at the University of Michigan, in transition to the University of Washington, and while transitioning, spending some time at Google Systems Research. So that's why I have this sort of monstrous affiliation. So I was supposed to be there. In fact, I was about to head to the airport, and unfortunately, my dog got sick, and I with no one to take care of her, and I had to unfortunately cancel my flight, take care of her. She's doing better. She's recovering. She's still very tired, but it was pretty scary for me. So again, thanks for giving me the option to do this remotely. Really appreciate it. So this talk is going to be about some of the work that we do in my lab to build efficient and trustworthy systems, and we're gonna really talk about efficiency first, and then sort of transition to trustworthiness, and I'll try to illustrate like how those two themes come together in my work, and sort of relate to the theme of the workshop as well. Feel free to interrupt me anytime. I think I should be able to hear you. If you raise your hand, I should be able to see you as well. I can pretty much see the field of view of the camera. So let's get started. So yeah, as I said, I'll talk about some of the work that we do in my lab to build efficient and trustworthy systems. And really, efficiency and trustworthiness are the two most basic expectations that users have of computer systems, right? So users want efficiency, right? They want their computers to have good performance and run fast. At the same time, they want trustworthiness, right? That's a combination of reliability and security, right? No one wants their computer to crash or to have someone break into their bank account. And although these two properties and expectations are very basic, the quest for them seems to be perpetual. Now, a key driver of this quest is data growth, which feels increasingly more complex and feature-rich software that uses this massive amount of data. About every 2 years, we double the amount of data that we've created in all of human history. And this trend will actually continue. And to keep up, we need to improve the efficiency of computer systems across the entire stack. Now, unfortunately, on the flip side, trustworthiness is often an afterthought. Software is plagued with bugs that cause data loss and outages, and critical vulnerabilities in hardware lead to serious security issues across the system stack. As a result, the total toll of poor software quality was about $2 trillion in 2021 in the US alone. Now, given these trends, improving the efficiency and trustworthiness of computer systems is paramount, and it's why it actually defines my research agenda. But it's also difficult, as these two properties are often in strong tension. Take antivirus software, for example. It improves, or it's supposed to improve, the security and therefore trustworthiness of your computer systems, but it slows them down, so it hurts efficiency. Now, at a high level, my approach to coping with this tension relies on developing a systematic understanding of program behavior and designing efficient and trustworthy systems based on this understanding. So what sets the work we do in my group apart is that I treat both efficiency and trustworthiness as first-class concerns and closely navigate the tension between these two properties. This requires our work to draw inspiration from diverse areas, spanning multiple layers of the computing stack, such as operating systems, computer architecture, programming languages, and security. And our work appears in major venues in all these areas. The overarching principle that we try to follow in our group is to strive for scientific and societal impact. So as I mentioned a minute ago, for each of these thrusts, my approach is to develop a systematic understanding of program behavior and build systems based on this understanding. More specifically, this involves a careful combination and balance of offline techniques and online techniques to navigate this tension between efficiency and trustworthiness. Striking this balance is a recurring theme that defines my group's work and approach to problems. So in the rest of the talk for each of these thrusts, I'll discuss what this balance looks like. And one thing we'll see is that some of the techniques that we use to improve efficiency can actually be simultaneously used to improve trustworthiness and hopefully dispel some of the notion that these two properties are always in tension. So we'll start with our efforts to improve the efficiency of data center systems, where our work on lightweight profiling techniques provide ample data to perform optimizations. All right, so data centers are, of course, massive geo-distributed computers that power a lot of the key internet services that we depend on and use all the time, right, such as web search. And they consume a lot of electricity, about 3% of world's electricity, which is a little more than what the UK consumes. A fascinating data point, in my opinion. It contributes, this whole thing contributes substantially to the global carbon footprint. And of course, data center operators can save millions with more efficient infrastructure, but also indirectly by increasing the responsiveness of their services, they can further improve user experience and increase revenue substantially. Now, seeing these potential benefits of these improvements, companies that operate large data centers have built a number of systems that continuously profile software using hardware support to, for example, track the branches that the program executes, right? They then use this information to power what's called profile-guided optimizations. So, for example, these optimizations may decide to reorder some functions to make the execution of the code more cache-friendly. So while profile-guided optimizations took off, a rich body of computer architecture research proposals have been developed to improve the performance of processors, right? These are techniques to, for example, cleverly prefetch cache lines. These optimizations use some on-chip storage to learn patterns of program behavior in order to power optimizations. Unfortunately, these proposals have key limitations, such as requiring significant hardware modifications, a lot of on-chip metadata storage, and providing limited speedups ultimately, because they can only rely on limited storage for the data that informs these optimizations. So as a result, a few of these approaches got adopted in modern hardware, but most did not. So we have these two trends. On the one hand, there's this rise of successful profile-guided software optimizations. And on the other hand, there's some great research aimed to do on-chip analysis and optimizations that's getting somehow limited traction. Now, our research on data center efficiency aims to combine the best of these two trends. Specifically, we develop techniques to efficiently profile programs as they're run in a data center to understand their behavior, right? That's the first step. Then, rather than doing the expensive analysis task inside the processor, we instead use the rich profiling information to do the analysis offline in software. We then apply optimizations to software as well as hardware. One of our key contributions is that because our profiling techniques are very efficient, we can collect and use a lot more data than can be stored in hardware, which enables very effective optimizations that weren't possible to explore before. Now, the techniques that we've developed are pretty effective. For example, for one technique, we've demonstrated that we can obtain 90% of the theoretical speedup that can be achieved. A key benefit is that some of our techniques require no hardware modifications, so they can be readily deployed in today's data centers. And for the cases that require a few hardware modifications, together with Intel and ARM, we're exploring the redesign of their future processors. And there's some recent updates on that as well, I'll talk about. So one such profile-guided hardware-software optimization is called iSpy, which is an instruction cache prefetching technique that I'll tell you more about today. So instruction prefetching is about anticipating which instructions the program will execute in the future and bringing them into the processor's cache ahead of time to improve performance. So you might ask, why do we need yet another instruction prefetching technique? So let me try to answer that. So we looked at some major data center applications used in companies, including Twitter, Netflix, and Meta. And what we saw is that these applications lose about 20 to 70% of all CPU cycles due to instruction cache misses. And the main reason behind these misses is the very large footprint of these applications that are up to 45 times larger than the instruction cache size. So this is a huge problem for data center operators. So as a result, there have been prior techniques that aim to address this issue. So here I'll show just one example to illustrate one such technique. In this example, each box will denote a function. So transitions among boxes happen via function calls. So a recent technique from Google works by identifying a function whose execution can predict the future instruction cache miss. So here, let's say this happens to be function D. This technique then introduces a prefetch instruction that will prefetch the cache lines of function G ahead of time. So by the time that G executes, it will not incur cache misses, right? And this is used, this is implemented using compiler instrumentation, meaning that once the prefetch instruction is inserted, the code will be recompiled and redeployed in production. But programs have complex logic, and this naive strategy doesn't really work well in all cases. So in this example, the function G is actually only called if the condition is 1 is true. And so now if we look further back in the program, we see that there is another if statement where if both conditions 1 and 2 are true, this other function B is called. So on this program path, it makes perfect sense to prefetch the cache lines of G, since we know that condition 1 is true if B was called, right? However, consider another function E, which calls function D only if condition 1 is false, right? Of course, we can see that if we follow a program path from function E to F, since condition 1 is false, function G will never be called. So on this path, the prefetch is completely unnecessary since G will never execute. So what we see is that the prior work was essentially overfitting the placement of these prefetches to execution profiles with limited runtime information, which results in unnecessary prefetches that result in poor cache utilization and limited speedups. So our work, iSpy, performs prefetching conditionally depending on the program context, right? So we determine context by considering a program's execution paths. And in this example, we make this prefetch conditional on the execution of function B. And the actual implementation, to compute the context, iSpy uses branches that the code executes, right? So that's the control flow of the program. iSpy collects branch information using online hardware tracing in a data center. And this kind of information is routinely monitored in modern data centers today. So iSpy merely takes advantage of this already collected telemetry. So using about only 4 branches to compute the context, we can obtain 90% of the speedup of an ideal cache. And by an ideal cache, I mean a cache that doesn't incur any misses, right? So every time you look up, you're going to hit in the cache. That's the theoretical best case scenario you can have. So in summary, iSpy is a hybrid software hardware prefetching technique that uses context-driven conditional prefetching. It's a data-driven optimization powered by offline analysis of profiling information. It avoids unnecessary prefetches and can be implemented with minor hardware support. It provides 90% of the speed up that an ideal cache could provide, And it outperforms the prior state-of-the-art proposal of Google by 22.5%, which, roughly corresponds to $700 million in data center operating cost savings. So we've built a number of efficient profiling and optimization techniques for prefetching, cache replacement, branch target replacement, and obtained similarly good results. So this has been a really fruitful area. Just to sum up this portion, I just want to iterate that improving the efficiency of data centers will reduce cloud provider expenses, improve user experience, and have a positive environmental impact. So we've had a lot of engagement here from different stakeholders. I think that the most notable thing I'll say here is that, for instance, Intel has actually just recently published that it's incorporating this conditional prefetching instruction into its ISA, and ARM is actually directly using some of the profiling techniques that I didn't get a chance to talk about in this portion of the talk for their high-end server systems. So if there are any quick questions for this first part, I can take them, or otherwise I can move on and can take questions later as well.
Hello.
Hello.
So, if we look at a slightly different problem setting in the HPC world, we have similar issues with, not so much branch mispredictions by Dcache problems. And we know that general purpose compilers really don't do anything about this nowadays. And as your work and others before had shown that compilers don't do anything about the other side of the coin, the iCache misses. So is there any hope that we can solve this problem without relying on any profile information? Or do we give up the same way that the HPC people have given up and they use a completely different way of solving things?
That's a good question. So I do, in some sense, I do not necessarily think that profile-guided optimizations are that much decoupled from the compiler, right? So really the profiling information feeds into the decisions that you make in how you reorganize code statically. So it's really just another source of information. But if you mean purely static without incorporating any runtime information, that seems tough. And what I'll tell you is actually profile-guided optimizations, as you might guess, themselves are not enough, right? Because the programs go through phases, their inputs change, and you can optimize the program for a given set of inputs. But as things evolve, as the program evolves and as the inputs evolve, there's still a gap that you'll need to close. And this is actually, we just talked about this work, this micro, like a few days back. So we have some work on actually dynamically incorporating profile information and modifying the code at runtime to actually incorporate some of this sort of, this behavior that sort of like changes throughout the program execution. There's still limitations. We can, for instance, only do it for one time, right? We can't do it. We can't keep doing it. We still have some limitations. It's early days, but I think there's stages of this. To what extent you incorporate dynamic information? I feel like you need to incorporate more and more depending on the behavior of the application. That's a great question. All right. Okay, I'll move ahead, and then if there are other questions, we can take them in the later portion. So, as we saw in my group, we do research for improving the efficiency of computer systems, which is what we talked about so far. But recall that the other basic expectation that users of computer systems have is trustworthiness. So we'll shift gears from efficiency a little bit and focus on some of the techniques that my group developed in the trustworthiness space, specifically with respect to software reliability. In this space, we've built widely deployed systems using a combination of offline program analysis and online program monitoring. More concretely, I'm going to focus on failure reproduction, which I argue is at the heart of software reliability. And I'll tell you why it is so. So some years ago, a paper from Microsoft Research showed that developers can fix any bug if they can reproduce the associated failure. And most of us, pretty much anyone in this room, right, that write code know this is true, right? So if we can reproduce a failure, we can often fix it. But reproducing failures is quite difficult, and especially so if those failures occur in production systems and the production environment cannot be recreated in-house during testing and debugging. So in traditional debugging, when a failure occurs on a user's machine, a report that contains the memory dump of the program is sent to a developer who must manually reproduce the failure and debug the problem, which may be hard or impossible, as we just said. Note that here I'm talking about sort of observable failures, such as failures like a crash or a hang. So as I just explained for our work on data center efficiency, information such as the branches that the program executes is routinely monitored to enable performance optimizations. These branches are kept in a buffer in memory, so if the program fails, the memory dump also contains these branches, which is effectively a trace of the control flow of the program right before it fails. So our idea that we pursued in this space is, well, we can use this trace as well as the last state in memory and some other information that we'll talk about in a bit to automatically reproduce bits and pieces of the failing execution so that the developer can easily debug their program. Now, using the same branch traces, both for optimizations and for bug reproduction, is a prime example of how my group's work actually navigates this tension between efficiency and trustworthiness. So we built two major systems towards this goal. Repeat was the first system for bug reproduction that we've developed in collaboration with Microsoft Research. Repeat is the most widely deployed failure reproduction and analysis system in the world. It's used in about 1 billion Windows systems. And more recently, my group developed a new technique called execution reconstruction, or ER for short, which combines offline symbolic program analysis with online selective hardware monitoring of both data and control flow information to reproduce arbitrarily longer executions than Repeat can. So I'll tell you a little more about execution reconstruction today, and to explain where our work on execution reconstruction fits, let's first have a look at the spectrum of failure reproduction techniques. So to understand what really happened in production, one extreme is to record everything, right? So thread schedules, inputs, etc. This approach leads to high runtime overhead, but can reproduce all kinds of failures, of course. The other extreme is to record nothing and rely on offline program analysis techniques like symbolic execution to reduce failures. This approach doesn't incur overhead, which is good, but cannot reproduce complex failures in real-world software. There's other work making trade-offs along the spectrum, but they have one of the two limitations, right? They either lean towards the record everything side and incur too much overhead, or lean towards the record nothing side, and therefore they're not necessarily effective in reproducing complex failures. Now, based on our study of prior work, we determined that existing trade-offs are insufficient to effectively and efficiently reproduce production failures. So we build execution reconstruction, right, ER for short, which explores the sweet spot in this trade-off space. So as shown on the spectrum with ER, we want to record some information, but we don't want to record all of the information, which would mean that we'll obtain a partial trace of the failing execution. But to reproduce a failure and give developers a replayable failure trace, we need the full trace. Now, recall that on the left-hand side of the spectrum, symbolic execution was used in fully offline tools where there wasn't even a partial trace available to reproduce a failure. So we asked ourselves whether we can generate the full failure trace if we just take symbolic execution and throw it at the partial trace of the control flow of the program, which is anyways collected for performance optimization reasons. Now, I'll show that this approach doesn't work, but before we get there, let me do a quick refresher on symbolic execution. This may actually not be needed for this crowd, but nevertheless, for the sake of completeness, let's do a quick refresher. So the key idea in symbolic execution is to run the program with a symbolic, that is unknown input values, and explore different program paths whenever a conditional is encountered. So in this example, X is symbolic, so it's unknown. Whenever symbolic execution encounters a branch that depends on symbolic input, it forks the exploration into two states and keeps track of what's called path constraints in each state. So here on one path, the path constraint is that Vx is greater than 0, and on the other path, it's less than or equal to 0. As symbolic execution proceeds, it encounters more and more conditionals, so it forks the exploration over and over again. Whenever an event of interest occurs in a state, say a program crashes due to a failure, the path constraint in that state can be plugged into an SMT solver, and the SMT solver determines concrete input values that satisfy the path constraint. And this is, of course, very useful because now you can use these inputs to reproduce and debug the failure. This brings us to the first problem with symbolic execution, the notorious path explosion problem, where this exploration results in a number of paths that's exponential in the number of branches that are predicated on symbolic input. Now, to solve the path explosion challenge, ER uses a technique that we call shepherded symbolic execution, which basically follows the control flow trace recorded in hardware using hardware support in production, right? How does this help with path explosion? Well, shepherded symbolic execution only follows the recorded control flow path to reproduce the failure. So there's no path explosion at all. So we're done, right? This, well, that would have been great, but as I hinted, that's not the case. Recall that there's another important component of symbolic execution, and that's invoking an SMT solver every now and then. And this is particularly challenging because SMT solving is a computationally hard problem, right? Or more specifically, NP complete for the theories that we're interested in. And SMT solving is so hard for complex programs that despite avoiding path explosion with a control flow trace, you know, the SMT solver will almost always time out after 24 hours in our experiments if we basically attempted to reproduce real world failures. So to alleviate this issue, in addition to the control flow trace, ER records what we call key data values that have the potential to speed up constraint solving using the same hardware, same kind of hardware support. The key question, of course, is how to determine the key values that can best simplify constraints and speed up constraint solving. Well, recall that SMT solving is NP complete, so we won't be able to efficiently find the optimal set of data values that will help solve an arbitrary constraint in the fastest possible way. Instead, based on empirical data, we observe that reasoning about memory aliasing takes the most time in symbolic execution. This is literally profiling the symbolic execution engine, right? That's how we learn this information. So symbolic execution will encounter many symbolic, that's unknown memory addresses. For example, consider two such addresses, X and Y, and to correctly keep track of constraints on memory objects during symbolic execution, like these gray boxes here, whenever a write to address Y occurs, the solver has to determine if Y may point to the same address as X, or in other words, whether X may alias Y. Memory aliasing leads to complex constraints, especially in real programs where there may be thousands or even more memory accesses that may alias each other. Based on these observations, we came up with the hypothesis that recording addresses will simplify constraints and speed up constraint solving. So we'll dig this into this hypothesis a little bit more right now. So to understand how to simplify memory aliasing during symbolic execution, let's look at this example at the bottom left. So there's this function foo in line 1 taking two arguments X and Y. We'll assume that X and Y are symbolic inputs here, so we don't know their value. We're trying to determine their value. And for better illustration, let us visualize the corresponding path constraints as a graph. And in this graph representation, nodes are going to represent the value of a symbolic expression, and edges are going to point from an expression to its operands. In other words, the source of the edge depends on the target of the edge. Now, in the constraint graph, we first have an array V from line 2, right? So this is a zero initialized array of 256 elements. Then we write to this array V on line 3 at offset X with constant value 1. Later, we perform a symbolic memory read from array V at offset Y on line 4. And remember that the array V was previously updated by the previous write. The symbolic memory read is then used as part of other constraints. And as the program executes, this constraint graph grows, capturing more dependencies and so on. And for a real world program, this graph will look much, much larger, of course. Okay, so the reason about, let's say, this particular symbolic memory read operation, the solver needs to consider the may alias relation between X and Y. X and Y may alias because they can potentially be any value. Remember, they're symbolic, right? They're unconstrained. And they're also used as memory addresses to access the same array, to index into the same array V. So the symbolic memory read may actually read the value written by the symbolic memory write, right? That's a possibility. So we find that reasoning about memory aliasing here can further be simplified by recording additional data values in production, like the address X. So here, we'll assume that the runtime value of X is X prime, and we're going to record that constant value X prime when the program executes in production, right? This can be happening when there's a failure that's occurring, of course, right? Now, this effectively allows cutting the constraint graph into 2 partitions, which are individually easier to reason about than the initial graph. On the left-hand side of the graph, the write and the read operations have to only reason about the concrete value of X prime. And on the right-hand side of the graph, ER can actually eliminate the symbolic memory write, right? So if you can see my pointer, I'm talking about this right here, the symbolic memory write, because all of the operands of the write are now constant values, right? The array, 0 initialized, 256 elements, a constant value. 1, the value we're writing, that's constant. And now we've recorded the value of X to be X prime as a constant value. So all those are constant. So we can create this, ER can create this new array, V prime, which is essentially the same array as V, except value 1 was written at address X prime. And as a result, now ER has to only need to think about the symbolic memory read at offset Y, which is on the bottom right of this figure, which is individually an easier task. Now, ER could record many symbolic memory addresses, but it uses 2 heuristics to identify and record key symbolic memory addresses. ER will record memory addresses used in the longest symbolic write chain and the write chain that accesses the largest symbolic memory object. And I'll explain the rationale behind these in a second. So in this example, there are 3 symbolic arrays, and each is associated with some symbolic memory operations. ER will record the memory addresses in the chain that accesses V1, since V1 has the longest chain of writes. The intuition here is that the more writes there are, the more aliasing relations that the solver needs to reason about, and recall that that's a main source of solver bottlenecks. Is this always the case? Of course, it's not always the case, but it is a heuristic that we end up finding out that it works really well in practice. ER will also record memory addresses used in the chain that accesses V3, which is the largest symbolic array. And the intuition here is that the larger a symbolic object is, the more memory locations the solver needs to reason about when realizing aliasing queries. In this example, ER will leave the handling of the chain that accesses V2 to the SMT solver without recording any addresses. So to recap, ER has an online tracing component to collect the partial trace and an offline analysis engine to reproduce the failure. In production, ER uses hardware support to trace the target application with low runtime overhead. When a failure occurs for the first time, ER will provide the control flow trace to drive offline shepherded symbolic execution. If ER is successful, then it's done. If not, ER uses constraint simplification and asks for more key data values to be recorded using the same kind of hardware support. So the next time around, shepherded symbolic execution will use the recorded control flow and the data values. So this is an iterative process between online hardware tracing and offline symbolic execution. And the iteration is going to stop when ER successfully reproduces the failure. Now, ER can rely on this being an iterative process because in practice, failures do reoccur, especially if you're looking at them at scale, right? Such as in the case of a data center operator. So I want to contrast ER to our prior work, Repeat, which is the system that I mentioned was deployed at Microsoft. And I didn't talk about the technical details of Repeat, but basically Repeat uses the control flow trace of the program to reproduce failures using some static analysis. But due to imprecisions in this analysis, it can reproduce executions that have tens of thousands of instructions. On the other hand, ER records the control flow and a few data addresses to power its analysis. And by recording the same total amount of information as Repeat, it can reproduce executions that are tens of millions of instructions long, which shows that the analysis of ER is more capable than Repeats. It is also, of course, more expensive, but it is nevertheless more capable. It's not like if you could run Repeat for longer, it would actually achieve a better result. So there are many more details, such as how ER employs a graph algorithm to minimize the amount of data that it records in production, and how it handles concurrency, which is a whole other subject of its own, which are all in the paper. But just to summarize some key results, ER eliminates path explosion and simplifies constraint solving and symbolic execution. And it can reproduce failures in long executions, such as up to 1,000 times longer than Repeat in our evaluation, without really needing to record a longer trace. This is extremely useful for dealing with failures where the root cause of the failure is far away from the symptom of the failure, which are often the more complex cases. ER does this on average with 3.5 failure reoccurrences and incurs a negligible overhead of 0.3% runtime performance overhead. Again, so just to summarize this portion, improving the debugging experience for developers has a huge impact on improving the positive the software quality and cutting maintenance costs. And again, part of the thing that I appreciate the most about this line of work is again, we had a chance to actually impact the real world deployment in Windows, and as well as helping with adoptions of our technology in companies such as Meta and Intel, which is really something that as I said, is important to the folks in the group. All right, so any questions on this second part? Otherwise, I'll talk a little bit about some of our work on security.
Sure. So, I have a very simple question. You mentioned about this constraint simplification. Remind me a little bit of concolic testing. Right?
Yes, that's a great question. What's the difference? Is that the question?
Yeah, I'm just trying to understand whether that's the same thing or it's somewhat different. Yeah.
Yes. So it's very similar, right, conceptually. So the main difference is in the use case. So in concolic testing, we make the assumption that we know the input a priori. We have an input that can drive the program down a certain path. We collect constraints, and then we flip those constraints to create new test cases, use it in fuzzing, etc. And it's a very valuable tool. In this case, we don't know what the program inputs are. This is a failure that occurred out there in the wild, and we're trying to determine the program input. So we're sort of working backwards. So there is a conceptual overlap, but the setup is quite a bit different, and it impacts the way we approach the problem quite a bit.
Oh, okay, yeah, thanks a lot. Yeah, it's really impressive, deployed on a billing systems. Yeah. Great.
Yeah, thank you, thanks. All right, so let me switch over to the last bit. So bug reproduction is about reliability, as we said, and the last bit of technical work that I'll briefly talk about in the trustworthiness space is on our efforts to improve hardware security. Here, we rely on a thorough classification of attack vectors that power defenses that are specific to different different threat models. So in 2018, after the discovery of the Spectre and Meltdown attack, our group discovered the Foreshadow vulnerability, otherwise known as the L1 terminal fault. Right? Foreshadow is a microarchitectural side channel attack. It exploits the fact that programs leave traces in a CPU's microarchitecture, which an attacker can use to leak secrets, right? So the most severe implication of Foreshadow was that it undermined the fundamental cloud security properties by enabling an attacker to bypass the virtual memory abstraction and basically allow a virtual machine in a cloud environment to extract secrets from someone else's virtual machine. So Foreshadow and all early microarchitectural side channel attacks use the CPU cache as a side channel to extract secrets. So most early defenses also focused on blocking secret propagation through the cache. However, my group then reported the first non-cache microarchitectural attacks to Intel, which they weren't really interested, by the way, which is other structures, such as the branch target buffer to leak secrets. And there are many such channels that the attackers can use to extract secrets. However, most defenses were still focused on eliminating attackers' access to a specific channel. Now, our approach to this problem has been different. So we aim to stop these attacks in a principled and comprehensive way by reasoning about how data flows in the processor and stopping secrets from reaching these channels in the first place. Here, depending on the threat model that we're up against, we built several defenses that offer varying protection with associated overhead, which is yet again another example of where our work navigates the efficiency and trustworthiness tension. So one such comprehensive approach that we developed is called NDA, which stands for non-speculative data access, and it's a CPU design to stop speculative execution attacks. So as I said, there are different side channels that speculative execution attacks can be mounted from, and NDA's goal is to stop all such channels. Now here's the key insight behind NDA. All existing speculative execution attacks require a chain of dependent instructions to first access the secret and then transmit those secrets. If we can control data propagation in the CPU pipeline, if we can reason about that information flow, we can break these dependency chains, thereby thwarting the code sequences that are required to mount these attacks. This applies to all such attacks, right? That's important to note again. So how are these dependency chains formed in speculative execution attacks? So we did a systematic analysis of speculative execution attacks and determined that in all such attacks, attackers first access a secret by speculatively reading it. Then they speculatively transmit the secret via a channel like the cache. Then after speculation resolves, they recover the secret by using some sort of timing experiment. NDA provides a collection of defenses that can break this dependency chain in speculation, specifically between the access and the transmit phases. And NDA does this by only disallowing unsafe instructions to speculatively transmit secrets, and otherwise it does not interfere with speculation. If we interfere with speculation too much, it's disastrous for performance, as I'll talk about in a bit. So how does NDA decide which instructions are unsafe? Well, this is where a careful study of the threat models come into play. Broadly speaking, and simplifying a little bit for the sake of time, there are two major threat models in speculative execution attacks. In what's called Spectre-like attacks, the attacker uses a branch to steer the control of the program, and then during speculation, the attacker accesses and transmits the secret. Then after speculation, the attacker recovers the secret using some timing measurements, as we said. In what's called meltdown-like attacks, the attacker uses a forbidden access, such as an access into the kernel memory from user memory, right, which then triggers a fault to transmit secrets And later, the attacker recovers these secrets when the fault that's associated with this illegal access is being handled. So in Spectre-like attacks, each instruction after a branch can potentially be unsafe. And in meltdown-like attacks, all loads can potentially be unsafe, right? And that's more drastic, of course. So to bring it all together, during speculation, NDA allows unsafe operations to execute, meaning it allows accessing secrets, right? Let me repeat this bit. This is important. So NDA allows operations to execute, right? So execute in microarchitecture means you can start accessing the data, right? So execution is not the end of it. So we have to retire the instructions ultimately. So we can start accessing operations. We allow access, but it doesn't allow the effects of such instructions to be broadcast, right? That's the final stage of an execution pipeline. It doesn't allow these effects to be broadcast, that is, to be transmitted to other instructions if they are unsafe. And as we saw, what makes an instruction unsafe depends on the threat model. And in fact, NDA's policies are actually much finer grained than these two policies for which the details are in the paper. Overall, NDA policies are much more efficient than in-order execution. So if we just do in-order execution, which trivially eliminates these security issues, we have almost 5x slowdown, right? That's unacceptable. The NDA policy that defeats all known Spectre-like attacks incurs 10.7% overhead, and the policy that defeats meltdown-like attacks incurs 36% overhead. That's pretty high overhead, of course, but as we said, that's a more drastic case where all the loads can potentially be unsafe. So not only all this, but the NDA offers more comprehensive security than channel-specific defenses, making the NDA's defenses future-proof. This line of work, again, is important to improve the trustworthiness of the very foundation of computer systems, right? If hardware is not trustworthy, we cannot rely on anything. We cannot build abstractions. We cannot prove properties about the rest of our software if we cannot depend on a solid foundation in hardware. So this line of work directly impacted cloud vendors and CPU manufacturers to actually deploy mitigations against foreshadow that improve the security of cloud systems. Again, an interaction that I valued a lot. So if there are any questions for this last bit, I think it's more important to take them. I have some thoughts about where this work will go, but I think it's more interesting if there are questions. We can take those. But I can also continue. All right. So I'll say a few things about where I see this research going, and just in light of certain trends in the systems/architecture world that I think are going to be prominent, and then we can discuss if you have more questions. So we saw some of the work that we do in my group, and so we motivated this entire line of work with the data trends, right? Which will continue driving increased software complexity and the need for efficiency, right? These are long-term trends that are sort of there to stay. And these will only be sustainable, right? These trends will only be sustainable with increasing hardware heterogeneity, such as specialized computing units, denser memory, faster interconnects, numerous edge devices, which will all bring new challenges in achieving efficiency and trustworthiness. And my group will explore emerging and increasingly more relevant problems in computer systems due to these trends, looking at the problems through the lens of computer architecture, programming languages, and security. And for the broad directions that I discussed today, I'll just give a summary of the trends that I think are transformative, that will require us to really fundamentally innovate going forward. So on the data center efficiency front, a clear trend is increased memory, compute, and interconnect heterogeneity. Specifically, memory technologies are very diverse in capabilities and are deployed in distributed environments, in heterogeneous computing resources such as CPUs, FPGAs, etc. The first direction that I'm excited to explore in this space is rethinking profile-guided optimizations, right? The ones that we talked about such as the ones that we talked about in the first part of the talk, and rethinking them using hardware-software co-design. So these are related to placement, replacement, prefetching, etc. For example, I'm really excited to explore what would platform support and policies look like for optimizations targeted at tiered and heterogeneous memory, which is sort of the landscape that we're headed towards. This is an area that we're closely collaborating with Intel at the moment. The second direction that I like to explore is designing new systems abstractions for resource management in this new environment with disaggregated resources, right? So the current programming languages and operating system support is not necessarily flexible enough to perform efficient resource management in a disaggregated environment. I argue that we need a more data-centric model that allows for more proactive resource management. On the reliability front, I think two exciting trends are that, again, hardware heterogeneity and specialization is increasing. Meanwhile, pervasive profiling and monitoring of software has now become a norm, right? So, and this is mainly for performance reasons, as we saw in the first part of my talk. I think there's incredible potential for actually using such pervasive profiling and monitoring for improving software reliability, as we saw in the second part of my talk. In particular, we can learn a lot about software properties by observing production executions and use the knowledge learned to rethink our approach to trustworthiness, for instance, by using better prioritization techniques for approaches such as fuzzing. This is a direction that we're currently closely pursuing with Google. Another area that I'm interested in is developing techniques to build more reliable heterogeneous systems. For instance, FPGAs offer programmability capabilities that we can take advantage to embed failure-specific monitoring capabilities, which can then help developers diagnose failures more easily. And you can envision having such specialized monitoring and telemetry exposure capabilities, not just for correctness, but also for doing performance optimizations for these highly specialized heterogeneous computer systems. Overall, building better development techniques for heterogeneous systems is crucial for sustaining the increase for compute demand at a rapid pace. The real vision that I would hope to help realize is bridging the gap between hardware development, which traditionally happens at a very slow pace, and agile software development, which happens at a much faster pace, right? And there's a lot of work to be done, of course, in this intersection, right? So I will only be able to tackle some of them, but there's tons of work to be done in programming languages, compilers, etc. All right, so finally, in the security space, through attacks such as Foreshadow, it's become clear that isolation at the level of the microarchitecture is lacking, unlike, say, at the software level, where it's a well-understood security primitive. Moreover, recent work by major cloud providers indicates that intermittent hardware errors, such as bit flips or incorrect computation results in various computational units, are on the rise, right? You may have seen these papers from Facebook and Google recently. The one thing I'm looking forward to exploring is to what extent in this space, we can employ context isolation, right? Both temporal and spatial, at the microarchitectural level as a security primitive, right? So as I said, in the OS level, we understand and we use this kind of isolation pretty clearly, right? So memory address spaces, context switching, etc. But that's not so much the case in microarchitecture, where performance has always been king. We'll have to rethink that if we really care about the security of some of our systems. I'd also like to pursue techniques to eliminate or reduce hardware errors that I just mentioned, right? So for example, recently through a collaboration with Microsoft, we found out that even commodity cloud workloads are susceptible to bit flips in memory, which attackers can use to mount rowhammer style attacks. So we have recent paper at ISCA that was talking about this phenomenon where you just run a normal workload in a NUMA setup, and you can actually bring row activations, DRAM row activations, to a high enough level that it gets close to thresholds of row hammer or surpasses in certain cases. So we're looking to design techniques to provide better wear leveling for memory systems to avoid such issues. And this is notable because row hammer, we think of it as a security problem. But if you have regular workloads triggering row hammer-like behavior, or bit flips rather, then it becomes a reliability problem, and it becomes sort of all of a sudden much more pervasive. And yeah, so the techniques we're developing are I think, and others are developing, are slated to be more important because these issues are slated to be more prominent with increasing DRAM densities. I'm also interested in designing abstractions that can expose some silent errors to the upper layers of the system stack to better detect and deal with them. So this will be a good opportunity to rethink fundamental system design principles, such as the end-to-end principle, in light of new hardware error trends. All right, so all of this work is possible thanks to the people I've collaborated with over the years, researchers, colleagues, and of course, most importantly, members of my lab. Just to close up, I want to reemphasize that the overarching broad goal of our group has been to strive for a direct real-world impact, which is a guiding principle that in all that we do. And yeah, with that, I'd like to wrap it up. Again, thanks for giving me the opportunity for giving this talk remotely, and I'm happy to take any questions. Okay.
Yeah, great, Baris. Thanks for presenting to us a really impressive body of work. So any questions?
Great talk. I have a question about the third part, which is how combinable are these solutions? So for instance, if I want to protect my system against meltdown and Spectre attacks, is then the overhead just too big and I have to decide on one, or what's the situation there?
Yeah, so that's a great question. So if you want the full protection, right, first of all, the approaches are combinable, right? So you can combine the approaches, but if you want full protection, which the results are in the paper, the overhead accordingly increases to, I would say, levels which are not very sustainable unless you really care about security primarily. The level is too high. So it's part of the reason. So it's a great question, actually. So it's part of the reason why we had to refine threat models and define individual threat models and build tailored defenses so we can have reasonable overhead for a given threat model. So yeah.
Okay, thank you.
Yeah.
Thank you. Thank you for the talk. Question on the last section. You said that it's independent of what kind of side channel you have, but how do you know that for a different side channel there will be not different instructions that you need to consider unsafe? Or for example, if you think of something like power consumption, how do you know that the execution alone doesn't already leak the information?
Yeah. So this is a great point. So I was mainly referring to timing channels, right? So I should be more precise on that. So if you have physical access to the device and you can do power measurements, etc., then all of a sudden the threat model becomes extremely hard to deal with, right? And the bar for actually providing a foolproof, bulletproof defense is very, very high. So if you have physical access to the device and do those kinds of measurements, these approaches are not going to protect you. But I would argue that that's sort of like a really high bar to clear.
Fair.
Yeah.
Other questions for Baris? Okay. If not, Baris, let me ask you a question. I think later on you also mentioned at the beginning, when you talk about this performance improvement using profile-guided optimization, I was wondering, whether you can use this for fuzzing. But at the end, I think you mentioned that you want to do this together with Google. And the improvement that you got is about 20 to 30%, right? So in the sense, I want to know, how do you anticipate that really to give us a big improvement using that for fuzzing, right? I mean, 20 to 30%, that's great, but still may not give us a lot of help for fuzzing, from the fuzzing perspective.
Yeah. So I think with respect to fuzzing, the way at least we envision incorporating this is more sort of using fuzzing in some sense as a tool, like we've used symbolic execution to help reproduce really hard to reproduce in production failures, right? So it's one of the main challenges that I gathered from talking to people in industry is, and just spending some time there, is you can find a lot of bugs using fuzzing, and a lot of those will actually remain open. They won't be fixed. And the reason for that is, if you can't make a case for how serious this bug is, how realistic it is, then developers will not spend time triaging, right? Developer time is extremely expensive. So the main goal with respect to using profiling information to guide fuzzing is twofold. One, reproducing failures that occur in production. We know those are serious, right? That's one. The other one is helping us direct fuzzing efforts, right? Because ultimately it's a search problem, right? And there's limited budget. Helping us direct fuzzing in some sense, right? So it's like think of it as feedback-driven fuzzing, in a way that you have a higher likelihood of finding bugs that may occur in production, right? So by better understanding how production code works, how failures are distributed in production code. So it's really optimizing for finding bugs that will ultimately get fixed.
Okay, great. Thanks a lot. Yeah, let's thank Baris again for the great talk.